Dale. Today we are going to start our discussion on probability. And we're going to start sort of with the basics of probability. So first I want to just sort of talk about, what is a random phenomenon. A random phenomenon is something that we know all the possible outcomes of. We just don't know exactly which outcome is going to happen. So one of them that we are used to seeing is, of course, flipping a coin. We call it a fair coin because heads or tails is equally as likely to appear when you flip that coin. And we know that the two outcomes of flipping a coin are heads or tails. When you flip the coin, it's totally random which one comes up. We know the possibilities, we just don't know which one we're going to get. And so that's what, when we talk about random in this class, that's what we're talking about. We're talking about a scenario where there are a known set of possibilities. We just don't know which one's going to happen. And so a lot of people talk about the law of averages. Um, that's a no-no here. You know, a lot of people will say things like, we've had mild winters, so we're due a harsh winter. In this example here, um, your friend is flipping a coin, blah, 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 and we're wondering if we should expect a run of tails. Like if you get heads a lot, oh, I'm sorry, she saw 6 heads in a row. Does that mean that the coin owes you a tails? Well, the answer is no. The coin doesn't know which side it's landing on. It's equally as likely every single time you flip the coin to be heads or tails. And sometimes you can get a bunch of heads in a row, or you can get a bunch of tails in a row. So some people would say that the law of averages says that it should be tails next. Well, that's just not true. The coin doesn't know um, which side it's been landing on. What we want to talk about is the law of large numbers. And the law of large numbers talks about long run probability. So if we were to flip a coin 1,000,000 times, we know from experience that about 50% of the time the coin would turn up heads, about 50% of the time the coin would turn up tails. There might be long stretches in there where we get lots of heads in a row or lots of tails in a row, but eventually, if we do it enough times, we'll get about half of them to be heads and half of them to be tails. So the law of large numbers is what we concern ourselves with in this class. Some of this might be familiar to you, but it's worth going over. So we have a few types of probability. We have theoretical probability, which is sort of what I just talked about. Uh, this is the notation we're going to use, the probability, and we sort of used it a bit, of event A happening. That's what that means. It's sort of like a function. This says the probability of A happening. And so we know all of the possible outcomes. And a list of all the possible outcomes is what we would call the sample space. So for example, if we are rolling a 6-sided die, the possible outcomes would be 1, 2, 3, 4, 5, and 6. And if we want to know the probability of, let's say, event A is rolling a 2, well, we know there's one way to roll a 2. And so that's how we get a theoretical probability. Theoretically speaking, when I roll a die, there's a 1 in 6 chance, a 1/6 probability that we'll get a 2. Personal probability is something that's mentioned in the book, so I just want to mention it quickly. It's something where, like, based on your experience, I think we talked about this in a simulation one time where they said I have an 80% chance of answering a question right. and then we simulated that person taking a quiz. That's personal probability. That's something that's based on what you know about yourself, but it's not founded in any real fact. And so personal probability is something that we are going to avoid, but just know that's what that's called. And then there's empirical or experimental probability. That's when you actually collect data. So that's what we did when we did simulations. We found averages, but we also found the likelihood that something happened, and that was based on our simulation. That was us calculating an experimental or empirical probability. So we could do that too with like coin flips and um, dice rolling. So then we have some probability rules. Of course, a probability is always going to be reported as a number between 0 and 1. I typically take it out to 4 decimals. It's not a hard and fast rule, but what I like about that is if you do change it into a percent chance, you will then have two numbers after the decimal place. When I have a scenario like rolling a die, I have a sample space for that, and so there are 6 possibilities when I roll a 6-sided die. The probability of each of those 6 numbers coming up, when I add them together, all the possible outcomes will always add to 1. So you can never have a probability larger than 1. A probability of 1 is a certainty. A probability of 0 means it's definitely not going to happen. Anything in between, there's a chance it could happen, there's a chance it couldn't. So if we know the probability of something happening, then we know the probability of that thing not happening is 1 minus that thing. It's called the complement rule. And I'm going to show you examples of this that will make it more concrete. We'll also talk about the addition rule. This symbol means or. If we want to know the probability that event A or event B happens, well, we can just add their probabilities, only provided that they're disjoint. That means that they can't happen at the same time. They are mutually exclusive, is another way that we put that. If they are not disjoint or mutually exclusive, then we have to do something else, and we'll follow up with that in a later lesson. And then we have a multiplication rule. This symbol means and. I remember it means and because I can make it an A. And so if we want to know the probability that event A and B happen, then we could just multiply them. But of course, we have a qualifier there that they need to be independent events. That means that event A happening, or let me say it this way, the probability of event D is not changed by event A happening. So this is where we get into some, kind of an idea of replacement or not replacement, like we talked about with the deer and the salt licks. When they are not independent, there's a different thing we must do. And again, we'll talk about that in a different lesson. So let me just do a couple examples here, and then of course we'll do some in class together. These are straight from the chapter, which I will have on the Canvas modules. So in the beginning of the chapter, they talked about you driving to work, and you pass this intersection, and about 35% of the time, the light is green. So we can actually write that as a formal probability. The probability of the light being green is 0.35. Oh, and they actually wrote it there. So we want to know the probability that the light isn't green. Well, if the light is green 35% of the time, then anything else is the light not being green. And so we're looking for the complement of this scenario. So the probability of it not being green is simply 1 minus 0.35. So that is an example of the complement rule. So we add on to this that we find a probability that the light is yellow is about 0.04, so about 4% of the time it's yellow. And so we want to know the probability of the light being red. So we know that it's green about 35% of the time. We know that it's yellow about 4% of the time. So we could actually figure out the probability that it's not red by adding those two probabilities together. This is an OR probability. Green or, oops, sorry. And I knew my mistake right away because it looked like an A. The light can't be yellow and green at the same time, so these are disjoint events. They are mutually exclusive. They can only happen by themselves, not at the same time. So we can just add these probabilities together. So the probability of green plus the probability of yellow, and this might be a little bit more work than I need to show, but so 0.35 plus 0.04 gives me 0.39. So this is the probability of the light not being red. So the complement of that will be the probability of the light being red. So we can just then do 1 minus that and get 0.61. I have a couple more. So that was an example of the addition rule. We were able to add those probabilities because green and yellow are disjoint. They can't happen at the same time. So now we want to know the probability that the light is red on Monday and Tuesday. I'm just going to say red M and red P. So this is an and. They're independent of each other because we're just going to assume that the light on Monday is not affecting what the light is on Tuesday. And so when we have an and, that's the representation of the multiplication rule. So we can just take the probability of it being red on Monday and multiply that by the probability of it being red on Tuesday, which is 0.61 times 0.61, which is 0.3721. So we're able to multiply these probabilities to find the likelihood that they both happen. You hit a red light on Monday and Tuesday because they're independent of each other. Hitting a red light on Monday is not changing your probability of hitting the red light on Tuesday. And so I'm actually going to leave it there as to not do too much today. There's an example of each of those. Again, we have an example of the complement rule. We have an example of the addition rule, and we have an example of the multiplication rule. And of course, we went pretty fast here trying to get this all into a lesson, but we'll have plenty of time to do some examples in class together, answer questions if you have them, and then in later chapters, we will talk about what happens when they're not disjoint or they're not independent. So again, if you have questions, just make sure you are prepared to ask in class.